Okay, welcome back. Today I'm continuing the lectures on neutrinos, and for one more week I'll do neutrinos. So next week I'll actually talk about, I've introduced a lot of strange concepts and both surprising and unsolved problems, and you're going to get more of that today. And next week I'm going to concentrate a little bit more on the future, if you want, what approaches people are using, what projects are being built to try to resolve some of the big issues in neutrino physics that also relate to astrophysics, cosmology, and particle physics in the future. So there's a bunch of big, ambitious projects. Those I'll talk about next week. In a sense, today's lecture is difficult. Difficult for me, and it'll be difficult for you. So you have to be a little patient today. And the reason is that I'm going to talk about this incredible phenomenon called neutrino oscillations. But to do that, there's certain kind of phenomenology and mathematics and quantum physics and so forth that get put together to explain it. Some of you have different backgrounds, some don't have very much background in quantum physics or some of the other phenomenology that I'll use here. And maybe more seriously, this course has different from most college courses that I teach. You don't do any homework. I can't send you away to study these. I have to show you. But let me just say these notes are on the web. And so more than my other lectures, what I'll show you today and some of the formulas, you may not absorb all of it, but I decided to show you anyway. So I don't expect you to necessarily absorb it today. If you're frustrated and want to learn it more, just go to the notes. They'll be there careful, and I've put them together pretty carefully. So some of it's going to go a little bit fast, and I'm not expecting you to absorb it all. But I decided to do it by just hand waving rather than by showing you the actual phenomenology a little bit would be a cheat. So I will go through it. This is where we are. We're on the 10th out of 15 lectures that I'll be giving. And so it's January 16th. We have one more. It'll be neutrino physics next time. And as I say, it'll be lighter than this one if you get discouraged by today's lecture. And then in February, at the end of February, after we take the month off, we'll start on gravitational waves, my favorite subject, and some astrophysics and cosmology and some of the big open questions there. For the last few weeks, which will be fun. So this is where we are, one more lecture on neutrinos. So I've shown you that the fundamental particles in nature, the building blocks in nature, contain quarks, of which there's 6 that are shown on the top left of this here. And we've talked a lot about that and gone through some of the physics of that. We also have the charged, what we call leptons, that come about due to the radioactive decay or weak decay, the electron being the first one, but the partners, the muon and the tau lepton. And all of these behave in a way that you could just have one of these sets, and that would be all there was in nature, and the big puzzle is just a single puzzle, and that is, why are there 3? Why do we have 3 families of quarks and leptons instead of just one? This is what we would have if we just have radioactive decay and everything we know about, if we don't go to particle accelerators and create what there are. And there seem to be only 3 total. Over on the right, as you remember, are basically the force carriers, or what makes us have everything from strong interactions, which hold everything together, to radioactive decay and electromagnetic interactions and gravity itself. So that's on the right. And now we're concentrating on this one, and it is the most complex, mysterious, and interesting of the whole chart. And that's why I picked it out. And I think also the one that's leading us to the most insights for the future of understanding what matter is made of, how it interacts, and how the universe works. So this touches almost everything. But they're the most mysterious. So there's neutrinos everywhere, as I've shown you. They're made in every possible way. We've shown you in the last ones that, like for the quarks, there's 3 of them, and they're distinct from each other. That is, if we go to, they're labeled here as a letter nu with a little e, or one with a little mu, or one with a little tau. And if we create a neutrino related to something that has electrons, then it's this one. If we create it in something that's related to what's called the mu meson, then we have this one and this one. So we have 3 distinct, just like the other ones. And their neutrinos themselves are very kind of strange and mysterious, and we haven't yet talked about whether, for example, they have any mass at all. But today we'll deal with the fact that we know they have mass. But they have this peculiarity, which I'm coming to today, that makes the subject both fascinating but complicated, in that these behave as 3 discrete families that we don't know why there's 3, why there's only 3, why there isn't just one in nature. But the neutrinos, for a different reason, actually interact with each other. So they break this rule of just one family. And that's this phenomenon that I'm going to describe of what's called neutrino oscillations. What we mean by oscillations is that they go back and forth in the right circumstances between each other. So we have this peculiarity that you start with something that has an identity. You think you know what the identity is, but you let it go for some distance in space, and it changes its identity. And that's the phenomenon that we'll talk about today. We call it oscillations because it doesn't just change its identity in perpetuity. It changes its identity, but then it'll change it back again. And there's 3 of them, so it changes identity in the triangle. Maybe there's more than 3, which is another subject, question which I'll bring up. So let's move on. We think there's only 3. That is, these 3 in neutrinos, not more, because we measure this reaction here, the reaction of creating the so-called Z boson that's responsible for the weak interaction. And it has a certain width in nature. The width comes about by the possible ways it can decay into time. It's broader if it decays quickly, and if it doesn't, if it's more stable, it's narrower. I can predict how narrow it will be depending on how many ways it can decay. And from that, we can actually measure, without showing you the chart that I showed you, how many channels it has to decay into by how wide it is. And you can see the curves here, 3 different curves. And those curves depend on whether there's 2 final ways it can go into 2 neutrinos, that's the tallest one. Or if there's more, 3 neutrinos or 4 neutrinos, it gets shorter and fatter. And the actual data are the black points on top of it, along here. And you can see that it follows very well the middle one, which is 3 neutrinos. So if the world were simple and nice, like a textbook, then we would just conclude there's 3 neutrinos. And in fact, we measure it very well, because here's the number. Actually, if you take this and you fit it, how well it fits and how well you measure it, it's 2.99 plus 0.02. So it's pretty definitive that there's 3. And just as there were 3 families of quarks, so it all fit together nicely until a new puzzle arrives, which we'll come to. However, it's a big question whether we're talking about the quarks or we're talking about the neutrinos. Why there are 3 anyway? First, why there aren't only 1, and then why there are 3, or maybe there aren't 3, there's more, but we don't know how to look for them yet. So a big unanswered question for physicists is, first, why there are 3, and we don't have a good answer for that at all. In fact, we don't have any answer for it. It's just the way nature seems to come. And there's still a question for neutrinos, because they're a little different from the other particles, is for neutrinos, are there only 3, even though I showed you that data that seems to show very definitively that there are three and only three. And that's because you could have neutrinos that have some different characteristics. And so that's an open question, and we'll come back to that again. As I showed in the last lectures, neutrinos are absolutely everywhere. Not only are they the most prevalent particle in the universe, even though most people have trouble grappling with what the hell they are, photons are the most prevalent thing everywhere. Of course, light's everything here. The second most prevalent thing in the universe in terms of particles are neutrinos. They're made from almost anything, including our own bodies. So we make neutrinos, a lot of them, just by the interactions that are happening in our own bodies. But neutrinos come about from cosmic rays hitting the atmosphere. That's the top one I have here. They come about, as I spent the last lecture on, in the burning of the sun. I'm going to come back to that. They come about, and these numbers next to it are just how far away they are, how long it takes to get here from these different sources. They come about from the explosion of stars, or a so-called supernova. They come about from almost any sort of astrophysical phenomenon you read about in the newspapers. So when you pick up the newspaper and you read that somebody saw something new astrophysically, almost in any case, one of the most prevalent result is that they'll produce neutrinos. They're the most prevalent, probably the most interesting and important result of the early universe. So when we talk about really understanding the early universe, the ultimate tool, if it isn't gravitational waves, which we'll come to in the next lectures, it's neutrinos that give us the best handle on what happens in the early universe. Even if we talk about this Earth that we live in, to understand what's happening in the core of the Earth, deep inside the Earth, the best tool we really have, our best signature we really have, is the neutrinos that are being emitted from the interior of the Earth. Those are all natural ways to make neutrinos. We also are able to make them in the lab, and we make them in two primary ways. One is in nuclear reactors. It's a product of nuclear reactors. When you make a nuclear reactor and it makes power, a product of that is neutrinos, very low energy neutrinos. The second is any particle accelerator. When we study particle physics, makes undoubtedly particles that decay. When they decay, they give neutrinos. And so those are the man-made ways. As I show you the science, especially next week, I'll show you how we're going to use these bottom ones to actually quantitate, because we have more controls over what happens, to understand some of the open questions, which I'll talk about some today and some next week. So, first the sun. Last week I showed you how the sun burns, and we talked about the fact that at the center of the sun, the engine that makes it go, called fusion, produces neutrinos, we think, or thought. And one of the big accomplishments of the last decades was to actually detect not the neutrinos from the sun and then actually be able to image them. This is an image of the sun detecting neutrinos. So a detector was made that could see things in all directions, and then you look at those neutrinos and they point to this image, which is right where the sun is, which is definitive proof that what's happening in the sun is a process that's emitting not just light, but neutrinos, which brings us back to the fact that that gives us the clues how the sun burns inside, and it's what we call the fusion process. So what we expected since maybe the 1960s or so is that the way stars burn and our own star burns is through the same process, which is nuclear fusion. And we expected that to be true, and then people looked at all the ways we look at the sun optically and with telescopes and with special instruments. But the first experiments were developed to try to see neutrinos from the sun. And the first important one was done by Davis and collaborators in the 1960s. And they looked at this reaction, which I show at the top, a neutrino interacting with chlorine-37 That's basically cleaning fluid that you buy in the drugstore. And it makes an electron and argon-37. And what happened is that experiment was the first to actually detect that neutrinos did come from the sun. And it was an elaborate and a very important experiment done deep underground by Davis and his collaborators. And that was a wonderful triumph. Only the fact is that our best understanding of the physics then didn't match what they saw, what typically happens in physics. That is, a great discovery was made that actually they saw a tremendous triumph. They saw neutrinos from the sun. As I said, now we can even point and see what they look like. And yet, for some crazy reason, which was unexpected, the number was wrong. The measured number was shown here, 2.55 in some units that we use to describe the number that come from the sun. They're called solar neutrino units, SNU. And the calculated number, with errors on them, you can see, is 7.3, almost 3 times as high. And that was a puzzle that started developing as early as the first measurements of Davis. And the first measurements of Davis were a great triumph in actually seeing that how we saw the sun burn seemed to be right, and he was given the Nobel Prize in 2002 for understanding the burning process in the sun by directly detecting the neutrinos that came. Underneath that discovery was this puzzle that started to develop, that yes, it's true, we saw neutrinos, we've seen later experiments, the neutrinos do come from the sun, but the number is wrong. And let me reflect on that a little bit. So basically what happens is the sun at the very core of it has nature's equivalent to a fusion reactor, We don't know yet, by the way, how to make a fusion reactor ourselves. That's the attempt to do that is a project in Grenoble called ITER, and some other projects that were less, but that's the most ambitious one, to try for the first time to make a reaction that's fusion that would be much cleaner than a fission reactor, and a possible way to make power, endless power in the future, one of our big needs as human beings. So the sun already knows how to do it, and it basically happens in the core of the sun. And I showed you last time a little bit how we see from measuring the surface of the sun, wind that comes off the sun, a lot of things, measurements of the sun, everything points back to a consistent picture of a nuclear process in the very center of the sun, as shown here, creating neutrinos plus heat and other particles that radiate to the outside of the sun, and finally the light and heat that we're used to. However, we have this problem. The measured number is only 40% or so of the calculation. And that was true not just in 1968, but it happened over a period of a long time. So the 1968 experiment, which is a big vat of cleaning fluid in a deep mine underground in South Dakota, measured consistently this neutrino number over a period of 25 or 30 years, but it got this number, 2.55 instead of 7.3. And there were many other experiments of different type that came along after that in different ways found the same thing. What I show here is the actual calculation of the emitted neutrinos that come from the sun. But there's not just one process, not just one reaction. The fusion process creates different reactions. First and foremost is the reaction of 2 protons coming together and making the process. And it's the most dominant. This is a logarithmic scale this way. And so you can see the highest one by far is this one here. And the energy is this direction. So the most prevalent neutrinos that come out come from a nuclear process of two protons coming together, fusing together and making helium-4, helium-4 then making the fusion process. And that only goes up to something like 0.3 MeV. Other processes that happen after that in the fusion process make a little bit higher energy neutrinos that are shown in these different lines here, and they're less intense, there's less of them, and they have higher energy. And these different lines have been attacked in different experiments. So shown up here is there's an experiment using a material called gallium, and it's sensitive in this region, fluorine in this region. The one that I showed you having a focus on the neutrinos themselves is only high energy ones. It's a different region. All of those have been studied and were studied over a period of from 1968 to the present, basically. And this is a picture that's the calculations. So it's taking and calculating the nuclear physics from first principles of starting from two protons coming together and being the source of energy at the center of the sun. So a whole set of experiments were done looking at those different neutrinos at different energies, and they have one consistency, and that is that if I look at what's supposed to be there compared to what's seen, the ones that are seen are always about a third to a half what was expected. So it doesn't matter which of these neutrinos we look at in this plot here, whether we look at the ones that are out here, we look at the ones that were in here, they all see signals, special experiments, different techniques, but always too small. And so I recall going to many meetings where there were basically two contingents of physicists, ones who basically thought that this indicated something new that we didn't understand, and that is going to end up where I'm going to go in a little while, which is that neutrinos have a property that actually they don't all get here from the sun in the form that they were emitted. That was what the beginning of what I'm going to call neutrino oscillations. The second possibility, which was the more likely, is that despite the fact that we seem to be able to predict neutrinos from the sun, we can predict a lot about the sun, even including things like sunspots and all this stuff that I showed you last time, that there's something wrong with the calculations, that the nuclear physics really wasn't understood. And so most professional meetings that I went to for a period of 10 to 20 years were basically the nuclear physicists who were experts on these calculations defending themselves, or the particle physicists attacking them, or possibly a few of them saying, well, maybe there's something new we don't understand about neutrinos. And that turns out to be the bottom thing here, neutrino oscillations. So that's where we were until a set of experiments that have been done have shown that indeed we do have neutrino oscillations, this funny phenomenon that I'm going to talk about now. And that neutrino oscillations have all kinds of interesting and strange effects. And this was not predicted somehow out of fundamental theory. But the fundamental result is the neutrinos actually are not massless. So we could have had neutrinos be like photons, and that was the expectation. They didn't have any mass. But for some reason, they do have a little bit of mass. And that little bit of mass is what is the reason, or the ability, gives it the ability to do this change of identity that I'll talk about. So we have three kinds of neutrinos. I showed them to you. And they have the ability, which we didn't have for the quarks, to talk to each other, to change identity from one to another. And that's kind of what I'll talk about the rest of this lecture. Before I do that, let me point out again and emphasize, because it's a subject you may well find when you read a newspaper or a professional article or whatever you do, that sometime in the future we find that there are actually more than three neutrinos, despite the fact that there's only three kinds of quarks. And that's because neutrinos could come, and there's motivation for why they might, in forms that make them a little different, and they don't interact with the other particles. So despite the fact that I showed you a very nice curve saying it was 2.99 neutrinos, there could be a different kind of neutrino. For example, it could be very heavy, and if it's very heavy, it wouldn't have shown up in that, or it interacts in a different way, say only by gravity. And so there can be more neutrinos, and there's reason to think there might be more neutrinos in the sense that it would be a nice way to solve some problems that I'm not going to talk about in this course that exist theoretically in the subject of particle physics. It also is true, and I showed you a little bit of that, and I'm going to show you just the curves quickly. It's also true that there are actually experimental indications or an experimental endeavor that claims that they do see a neutrino beyond the 3 that we see. So I don't want to leave you with a clean picture that there's only 3. We don't really know. There's only 3 of the kind that we're talking about, that's for sure. So there's an experiment which sees another kind of neutrino. I talked about it briefly before, but I'm going to mention it again. It's called it's a series of experiments being done first at the Los Alamos Laboratory in New Mexico, and then at Fermilab. This is just a picture of it. It's a big vat, a big spherical vat being viewed by photosensitive devices called photomultiplier tubes, full of pure mineral oil, and looking at neutrino interactions that come from an accelerator. Without going through the details of these pictures here, you'll see the scale on the bottom is GeVs, not MEVs. I was showing you something in MEVs, so when I say there's choice of another neutrino, it may be very, very different, much, much heavier. And all the colored parts of the graph are basically all the things we know about, and yet the data is higher than that, so that there seems to be the possibility that these neutrinos, you start one way and you find that you have antineutrinos or neutrinos that come from the others. And this has been cited as evidence for another neutrino or more complicated, what I'll talk about the rest of this time and next time, neutrino oscillations. Because neutrino oscillations, as I drew them, were between these 3 neutrinos, and that's what I'll come back to 5 minutes from now. Instead, what I'm going to talk about for the rest of the time, because that's what's established once I finish talking about this first few minutes, is just this part down here. I'm going to revert to that in a few minutes. But instead, there's this possibility that there's another neutrino and a difference that's very big. The reason we don't see it is it's kind of off the other plots, and this is evidence of that, which is shown in a particular kind of plot, but shown in logarithmic scale here. This is the difference in mass, so it's very massive. It's thousands of times heavier than the other neutrinos. And there's been 2 experiments that see that, and they see a particular mass region. This is in my notes, so it's not ignored. But for the present time, everything I'll do after this is going to ignore the fact that there may be more neutrinos. It's something we have to find out in the future. And there even is some possibility that some have been observed. But not to complicate things, since that's all if, maybe, but, I'm going to pick the 3 neutrinos that we have and talk about the science then of these neutrinos and how they interact with each other and what we have to learn from this, which may include why we're here even, which I'll come to at the end. So in order to have neutrino oscillations, that is neutrinos changing identity, coming from the sun to us or coming from me to you if I'm emitting them, we have to have at least one of the neutrinos, something we didn't know before, for sure, has to have some mass. It's true mathematically. If they're all massless, they're not going to interact with each other. So some neutrino, at least one, has to have mass. We think, but we don't know, that all of them will have some finite mass. We're not sure of that. And I'm going to show you next week when I talk about future experiments. I'll show you the limits now on the mass, but I'll show you the ambitious project to determine what the lowest mass is of a neutrino, which is being done in Germany. So if they have mass, then it turns out that they have to mix. It turns out just in nature that what I show you has to happen. It isn't, we don't need a theory. Once they have some mass and they're different from each other, then the phenomena that I'll show you has to happen. So basically that's true. The oscillations themselves that I'll show you depend on what the difference is in mass between these neutrinos. How close they are in mass, what the difference is in mass. And that is what we're determining from some of the experiments that I'll show you. We know quite a bit now about the differences in the mass, but we don't yet know what the lowest mass is, except that we think it's finite. Since the oscillations depend on the change in the mass, we also have to determine two other things. What is the mass of the lightest neutrino? Saying it's not zero. We're not sure it's not zero. And that we do by looking at nuclear beta decay and finding the highest energy electron that comes out with this neutrino. And if the neutrino weighs a little bit, the highest energy is a little bit lower than if it doesn't weigh anything. So we look at the endpoint of the energy distribution of the neutrinos to determine that. And that's this big experiment that I'll show you next time. And the second is another puzzle, and which I didn't address, but matters a lot in terms of how you treat the neutrinos and what impact they have later. And that is, as much as you'd think we would know, we don't know whether the neutrino is its own antiparticle, or whether the antiparticle is different from the neutrino itself. So that's another unsolved problem. And there's a special kind of experiment to try to determine that called a double beta decay. And I'll come to that not today. So now I'm going to start on what's the harder part of this lecture. I'm going to wave some formulas at you. And as I say, they're in the notes. Just absorb whatever you can now. And don't worry too much if you can't follow all of what I say as I say it. So neutrino oscillations, the phenomenon of neutrino oscillations themselves, for a different reason than the data that I showed you now, actually for a false result, was first proposed by Bruno Pontecorvo in 1957. And that phenomenology that he did was also picked up by others later, and even by himself in developing the phenomenology that I'll show you. But what he realized is that if the neutrinos have finite mass, they're going to have this proclivity to change their identity from one to the other. So if you look at the formula up here, I start out with two kinds of neutrinos with these little subscripts, nu sub e and nu sub mu. Those were two of them in the columns that I had. But in reality, those are the ones that have the particular feature to be in one of those families, but they're not the particular, they don't have a unique mass. The unique mass states are a combination of two other nus that I call nu 1 and nu 2 here. And then the unknown part of how much of nu 1 and how much of nu 2 something is, we put in by putting an angle. So we have a cosine and a sine. And that's basically the relationship between the quantum families, neutrinos, and the mass, what we call eigenstates. So in a weak decay, we produce a definite weak eigenstate. That's a word from quantum mechanics, but I have to use it. So then in a state when I have the neutrino as a function of little t, that's time, it is, because of these angles, it's a combination of these two. So it's a combination of these two. We put those together, and we get a probability that an electron, a neutrino that starts as an electron neutrino, like at the middle of the sun, and look at it later to be another final neutrino as a function of time, is this formula here. It varies with time, it varies with how much energy difference there is between the two, and it varies with this unknown angle, which nature gives us, but we don't know it. So as I say, this is in my notes, so you can look at it. And the energy difference between the two neutrinos is given by this. And we end up with formulas that are the ones that you see in the literature. So the probability that I have a neutrino after some length L is given by this formula here. It's a product of a sine squared of an angle that we don't know. We have to measure the length that we go, what the difference in masses of the particles, how energetic they are. And that's the fundamental formula that I'll use in one form or another in the next few slides. The derivation of neutrino oscillations is similar but a little more complicated than what I showed before for strangeness oscillations or B meson oscillations. So I've shown both of those in the past, but they're not quite as complicated as this one. To make the derivation simple, we assume that CP is conserved and that there's only two kinds of neutrinos. So I showed you maybe there's more than two kinds of types of neutrinos. But we don't know. CP violation, or CP is conserved, is an interesting question. So for what I'm going to talk about here, we're going to assume that CP, this is symmetry in nature, charge and parity, symmetry when you look in the mirror, whether you see the same thing backwards or not. It turns out, and I'm going to come to it not in today's lecture, but in the future, that it's almost a given by physicists that try to explain what happened in the early universe such that we end up the way we are. That is, that we live in a matter-dominated universe. There's no antimatter that we see anywhere around us. Yet in the early universe, we expect that we should have made as much matter and antimatter by Einstein's equation. Energy becomes matter. So what created that asymmetry, we're not sure. But in our best present ideas of what created that asymmetry, there's two things that are required. One is that neutrinos have some sort of asymmetry themselves. I'm going to assume that asymmetry is zero right now, but some sort of asymmetry itself. And one of the biggest goals, which I'll talk about some next week, in neutrinos is to find out whether there is that asymmetry, whether when you look in a mirror, a neutrino doesn't have exact symmetry. The second requirement, we believe, in order to explain how we end up in a matter-dominated universe, or why we're here even, that it didn't just all annihilate, is that protons, the basic thing we're made out of, have to be unstable. Unstable means they have a finite lifetime, not infinite. We know that lifetime is at least 10 to the 35 years. It's pretty long, but it may be still unstable and longer than that. So those are the two ingredients that we presently, and I'm going to come to that in the last lecture probably. But for today, we're going to assume that CP is good. At the beginning, we start with an electron and a muon neutrino. We said those are the identifications, like the table that I gave you. But then they're mixtures of these mass, what I call eigenstates, nu1 and nu2. And they mix with some, mathematically, we just do it in terms of an angle, sines and cosines, to make the mixture between them. We don't know beforehand how the mixed neutrinos are, how they mix or how much, and that's why we just use an angle. We did this problem before, and it was simplified when I talked about K-mesons. It was when I talked about the mixture between two kaons, two kinds of kaons, the K1 and K2, for example. We didn't have to put this theta in because it was 45 degrees. So it just happened that it was a number, we put in the number. But here we have an angle. So one thing we have to determine is the angle. So the mass eigenstates That is, the muon neutrino, the nu1 and nu2 are what propagate through space with energy E1 and E2, and then by a formula that has this angle in it, because we don't know that it's, say, 45 degrees or something else. And they propagate through space. We're interested in the case where the neutrinos are relativistic, so they're very light anyway, so they're going to go near the speed of light. And we put that in, which I've done mathematically here, and then in contrast to the kaon case where it was 45 degrees, we leave this angle in. And assuming both neutrinos have the same energy, both components have the same energy, then we write down what the neutrino is as a function of the angle and energy and time. We get this equation, put it together, as I say, I'm putting this in for completeness. I'm not going to go through it in detail here. We get the formula finally that you see in the literature. That is, if we start from a neutrino that's a muon-like neutrino here, and you want to ask what's the probability sometime later that you find it as someplace later as an electron neutrino, then it's a function of this unknown angle that we have to measure. It's a function of how far it went. It's a function of what the mass difference is between the two neutrinos and what the energy is of the neutrino. And so you get this formula which describes it, and nature tells us when we measure it what that formula is. So that's the formula on the bottom, which is the common one that you see in the literature, which I've only outlined for you. And as I say, if you want to actually look at it, the notes will have you. I did it a little quickly. Then, usually, again, if you go in the literature and look at neutrino oscillations, people like to put it into yet a more mathematical formulation, and that is a matrix formulation. So if you want to put the whole problem together, you start with three kinds of neutrinos: the nu e, the nu mu, the nu tau. But we end up with these other neutrinos, which are mixtures of those, nu 1, nu 2, and nu 3. And to get from here to here is a matrix where these u's are unknown until you measure them, and they're measured in different ways. I indicate at the top that if you let things go a long ways, 15,000 kilometers in this case per GeV, you tend to isolate the terms over here. If you go a short distance, you isolate different terms. So experimentally, you can isolate the different terms and end up with what the form is of this matrix, and sometimes you see that in the literature. The next thing I'm going to point out, I'm not going to make a big deal out of, but it's again one of the contemporary most important problems, is that I had these three neutrinos, and then I have three masses associated with these. Is the mass ordering of these, whatever the masses are, is the mass ordering of these the same as going from the electron to the muon to the tau, or some other mass ordering? That's very controversial. So it turns out the mass ordering, if it's the normal mass ordering, it would be like the quarks. It would go from the lightest quark, whichever family it was, the electron muon, to the heavier one. The heavier one, it would look like this, or maybe it's inverted. Mathematically and data-wise, it could be either. And we haven't resolved whether we have what we call an inverted hierarchy or a normal hierarchy, and they have very different implications physics-wise. So one big open question which people are trying to resolve, and we're probably close to resolving that within less than 5 years, maybe even less, whether the ordering of the neutrino masses follows the ordering of the quark masses or somehow are inverted from each other. You would think logically it would follow the order, but there's no rule that makes that be true. And it turns out that the physics consequences are quite different in the two cases. So one big question in physics that people are pursuing and working very hard on right now is what they call the hierarchy. Is the mass now that we know there's masses for the neutrinos, are the masses ordering from lightest to heaviest the same as for the quarks, or are they somehow inverted from each other? And I show that here. So the best solution we have, taking all the data that people have right now, I summarize in this rather strange plot here. So the mass differences are shown going this way. And the fact that any given one isn't made up just of one kind of neutrino is shown by the color bars on here. So if I take this one down here, it's made up this much of this one, of the electron neutrinos, this much of muon neutrino, and this much of a tau neutrino. So it's got a mixed parentage or mixed ownership when you talk about kind of the quark families or what kind of neutrino label you give it, and yet its mass is a unique mass, which is the lightest one. This is the best solution, kind of drawn graphically from all the data. I'm going to show you a little bit of data, but from the data that we have. You can fit all the data just as well and come out with a figure on the right, which is the inverted hierarchy. And again, as I've pointed out for other things, it has very different physics consequences. So whether we have the normal hierarchy or the inverted hierarchy is one of the primary problems in particle physics and certainly in neutrino physics that people are trying to resolve. There's some preliminary results that I would say tend to favor the normal hierarchy instead of the inverted hierarchy, but it's far from definitive, and we know kind of from physics and history of physics that until you get a result that's definitive, you don't really know. So presently, that's one of the big things that people are working on. Okay, I think we should take a break, and then I'll continue.